Michael teVruugt. I'm a PhD student from Muenster doing a double PhD in physics and philosophy, and I'm actually going to report results from both sub-projects. And the topic will be dynamical density functional theory and the Mori Zwanzig formalism. This is work which I've done mostly together with my physics supervisor, Raphael Witkowski. But parts of this work have also been done together with Helmut Brandt, Sabine Hossenfelder, Julian Jägler, and Hartmut Löwen. We're based at the Institute of Theoretical Physics and the Center for Soft Nanoscience, which is a new research institute in Muenster. So this talk will have 4 main parts. Some of this will be, in particular, the first and the second one, so things that are known for some time. Some will be things that we have recently published, and some will be work in progress. And of course, I'd be particularly keen to have a discussion with you on the last part. So I'll talk about the Mori Zwanzig formalism in general and its application to standard DDFT in particular. Then I'll discuss extensions of the DDFT that are derived using Mori Zwanzig formalism, and later I'll talk a bit about philosophy. I'll start by explaining what the Mori Zwanzig formalism is. It's a method from non-equilibrium statistical mechanics, actually one of its central ones, and provides a coarse graining method. So the general idea is that all the observables describing a system form a Hilbert space, and the observables that you're interested in form a subspace, and then you can introduce a projection operator that projects the complete microscopic dynamics that you're not interested in onto the subdynamics of a set of so-called relevant variables that you can, in principle, choose whatever you want for. And the irrelevant part of the dynamics then appears as memory or noise terms. And an introduction to this method can be found in this article, which we've published in European Journal of Physics last year. So a standard and very instructive example is fluid mechanics, namely the derivation of the Navier-Stokes equation. So you start with the microscopic dynamics of a fluid given by Hamilton's equations. You say, okay, I'm not interested in where every single particle is and what its momentum is. I just want to know the total mass density and the total momentum density. So I choose this as my relevant variables, and I apply a suitable projection operator. I make some standard approximations, and then I pretty directly get the Navier-Stokes equations. And that, of course, shows what a powerful formalism this is.
Sorry,
yes?
Can I ask a quick question? Could you just briefly mention the approximations?
So the main approximation is the Markovian approximation here. So I'll talk about this on some later slides in more detail, but you first of all get an exact transport equation that has a memory kernel, and then you assume that in this case, mass and momentum density are slow variables, which here, for example, means that energy density is not, so the system is isothermal, and then you get closed dynamics for mass and momentum density. And you also probably need some more to make it to a local pressure functional. But I'll come to that for the example of DDFT on later slides.
Okay, thanks.
You're welcome. Yeah, so standard derivations typically assume that the Hamiltonian is time dependent, or more importantly, that the Liouville operator is time dependent. And if you have a system that is driven by time-dependent external potential, then the formalism has to be adapted. So some operator identities that are used in the derivation change a little bit. And also some expressions for the diffusion tensor change a little bit. And this we've discussed in this PRE from 2019. We've considered the case of classical, but also quantum systems, in particular the case far from equilibrium, which is less explored in this regard than the close to equilibrium case. Also, as a bit of a digression, the problem of coarse grain is, of course, not only relevant in soft matter physics, where we're all coming from, but it's also relevant in general relativity or astrophysics. So if you're doing cosmology, you're also looking for a large-scale description of the universe. You're not interested in where every single galaxy is. You just want to have sort of an average description. And what you're then usually doing in sort of an introductory general relativity lecture, and also in astrophysics as it is currently done, you're assuming that the density is homogeneous, so you're inserting the average density of the universe and insert this into the Einstein field equations and solve it, and this gives you the Friedmann equations. And it is known for quite a while that, strictly speaking, this is mathematically wrong, because the Einstein field equations are nonlinear. And so actually you need to do a proper coarse-grained procedure. And this issue can actually also be addressed using Mori-Zwanzig formalism, which we have done in this preprint here. And what's interesting about this for this conference is that actually the DDFT and cosmology can be treated within a very similar framework, and ideas that are actually mostly used in soft matter physics are coming from there can also be applied to this very different physical context and actually be used to derive some empirical predictions for the cosmic expansion. Now I'm coming to the derivations of DDFT. So I'm using here a picture from our review article to illustrate the various ways in which it can be done. So you can do it phenomenologically by saying, okay, it has to be the diffusion-like equation and it has to be driven by the gradient of a free energy. You can derive it, those are the two standard routes, so to say, from Langevin equations or from the Smolakowski equation. Or you can take a more microscopic starting point, namely by starting from the Hamilton equations, and then use the Mori-Zwanzig projection operator formalism. The Mori-Zwanzig formalism can also be used starting from here, but that's less common. And for now, I'll typically go to assume this route here. So the Mori-Zwanzig formalism allows to derive DDFT starting from a Hamiltonian dynamics of a many-particle system. And in that case, since it is the dynamic equation for the one-body density, we're using a projection operator that projects the microscopic dynamics onto the dynamics of the one-body density. And of course, one has to make the approximation I've discussed before, namely that the density is the only slow variable in the system, and this is what in this context the adiabatic approximation is. Such a derivation was performed by various authors, so the general idea was around already since 2000, I would say, but so the two standard derivations of this type, I would say, are from Yoshimori and from Espagnol and Löwen. And how this works is in the Mori-Zwanzig formalism in general. So I'm focusing here on Hamiltonian systems, but the formalism can also be applied more generally. Is you choose a set of relevant variables, and their mean values AI are then governed by this transport equation here. So the first term is the organized drift, which is the reversible part of the dynamics. Then we have here a memory term governed by this memory matrix here, and then we have a random force, or in this case, a mean random force. And then we commonly make two approximations. First of all, we assume that the relevant variables are slow, so that this memory kernel falls off quickly, and then we can get here this irreversible dynamics. And first of all, we have here a mean random force, and we make typically a certain assumption about the initial conditions, which has the effect that the mean of this random force vanishes with respect to the ensemble we're considering. So this is a transport equation for the mean values. So how can this be used to derive DDFT? Basically, you choose AI to be rho. You use the fact that this organized drift is typically vanishing for symmetry reasons if you only have one variable. You use the fact that this thermodynamic conjugate here can be expressed as a function derivative of the free energy. You exploit that the microscopic range of change can be written as a gradient of a current, so you exploit the conservation law. Then first of all, you get a non-local expression, and then you assume that the system is dilute, or you ignore hydrodynamic interactions, and then you arrive at this expression here. So the Mori-Zwanzig formalism comes in different variants. The one I'm focusing on here is the canonical method, where you fix the average values of the relevant variables, in analogy to the canonical ensemble, where you're specifying the temperature and thereby fixing the mean value of the energy. And this is what gives you deterministic DDFT. But as you probably all know, there's DDFT can also be derived in a stochastic framework, which has some subtle differences from the deterministic case, for example, regarding what the density means. And for that, you can use the microcanonical method, where the value of the derived variables is specified exactly. And this name is chosen in analogy to the microcanonical ensemble, where you fix the exact value of the energy. Okay, that was the first part. Now I'm coming to the extensions of DDFT, in particular to the framework of EDDFT, which simply means extended dynamical density functional theory. And the basic idea of this framework is, okay, we can derive DDFT using the Mori-Zwanzig formalism, and DDFT allows us to include in principle any variable we could think of. So if we want, for example, a theory that describes also non-isothermal systems, so also the energy density, we just repeat basically this derivation, but we extend our set of relevant variables to include also the energy density, for example. The general idea is still the same. Of course, the details get way more complicated, but in general, this is a very powerful framework. This has not only been done under the name DDFT, another approach under this general framework would be functional thermodynamics, for example, but I'm focusing here on the EDDFT. And energy density was actually the thing that was originally included in this paper here, where the idea was introduced and where thereby DDFT was generalized to the non-isothermal case. And in a later paper published in 2013, that framework was extended to include also the entropy density, and thereby get sort of microscopic arguments based on assuming the local validity of the first law of thermodynamics for the entropy production. But it was discussed already in this works here that in principle, this framework can be extended to arbitrary variables, and what we've done is to incorporate also the momentum density. Of course, we're not the first one to include the momentum density in the DDFT, and certainly also not the second one, but still it gives you, I would argue, certain new insights regarding important conceptual and technical aspects. I'll give some examples later. Okay, so a DDFT with momentum density can be derived by projection onto the mass and momentum density, but also by other means. One article that considered this was, for example, this one, where governing equations for both the mass density and the momentum density G have been derived. And in the reversible limit, those equations look like this. So you have here the continuity equation for the mass density and this equation for the momentum density. And various other articles arrive at expressions of this type. And what's interesting about this is that this is the transport equation for the momentum density, which is a conserved quantity in the microscopic dynamics, at least if you ignore damping. So if you start from the Hamiltonian dynamics. But still, this is not a continuity equation, so it's not really clear in what respect this satisfies momentum conservation, even though it, of course, should, because it's derived from a microscopic dynamics that does respect momentum conservation. And it has been something we've been thinking about for a while, and I would argue that you can actually show that this conserves the total momentum density because of the symmetries of this functional here, in particular because of the symmetries of the direct correlation function. So speaking about the momentum density, one can of course consider the momentum density also in active matter systems. So if shown before, we know the structure of transport equations in underdamped passive matter, and we also know what the transport equations look like in overdamped active matter. And that can give us a certain clue on how to derive the transport equations for underdamped active matter. Again, this is something people have started to look at in recent years, and we in particular have derived a phase field crystal model that describes active matter with both translational and rotational inertia. So you have a finite relaxation time for both translation and orient and angular momentum. And you can also allow this to be on different time scales. This has been done in this article published recently in New Journal of Physics. And it reveals several interesting effects that you wouldn't have in either underdamped passive or overdamped active matter. For example, the phase boundaries, if you look at the phase diagram, can depend on the friction coefficient. So it's not just going to the minimum of the free energy, but the friction actually determines whether the fluid state is stable or not. And also you can find different modes of sound propagation that contain as a limited case what is known about sound propagation in these two cases here. But now I'm coming back just to standard passive Hamiltonian dynamics and to this well-known transfer equation for the energy density. Because we want to include the momentum density, but of course we still want to include also the energy density, and including both is actually what makes things really difficult. So it is known from standard hydrodynamics, and it also comes out of this derivation that the energy density obeys this transport equation here. And it contains in particular this pressure tensor here. And so our dynamics is not incompressible, so the pressure is not just like a Lagrange multiplier. We actually need an expression for the pressure in terms of the density. And the challenge is then to get this expression for the pressure from DFT or DDFT. So first of all, what would we do in the isothermal case? In that case, we say, okay, DDFT gives us this here. And we also know in general the Euler equation, which can also be derived in the reversal limit from the Mori Zwanzig formalism, which looks like this. And if we compare these two, then we say, okay, the pressure tensor probably looks like this. So we have an inverse gradient and then rho red delta F bar delta rho. And something of this type was also done in this article here, and that gives us a very reasonable expression for the pressure tensor in the underdamped fluid, in the isothermal fluid. The question is, what can we do with that in this case here, where we explicitly, if we multiply that out, require the pressure tensor. So it works in the isothermal case, what I've shown before, but it doesn't work out in the non-isothermal one. Because in a non-isothermal one, you can take the ideal gas limit. In that case, everything is exactly known, and the result doesn't really look like this. Or it does almost look like this, but only almost. And that has to do with the fact that in the non-isothermal case, the natural thermodynamic function to consider is not the entropy. It is not the free energy, but the entropy. From that, we can perform a Legendre transformation to a free energy, but that free energy is dimensionless. So we would typically make it dimensional by multiplying it by kBt, but if t is a function of space and time, then we actually have to be careful with where to put the t in front or after the gradient. One expression that would satisfy the correct isothermal and ideal gas limit, though not the only one, which is why we're going to check this with MV simulations, is this expression here. Or I can express it in terms of the density and a non-isothermal excess-free energy functional. Okay, what we then require, of course, is yes.
Can you hear me?
Yes, I can.
This thing that you're calling the pressure tensor, I mean, when you derive it in microscopic series, Isn't it really the stress tensor, and shouldn't there be
Yes.
dissipation as well?
Yes, it's the stress tensor.
But shouldn't there be dissipative terms like involving the viscosities and bulk compression?
Yes, as I mentioned before, I'm considering only the reversal limit at the moment.
Okay.
But of course, the dissipative terms also come out of this formalism. I'm just not showing them here because they're lengthy and
You can
missing.
talk about one part and not the other because they sort of come from the same thing.
You can, because as I've shown before, here, so you have, if you derive this general theory, the reversible part and the irreversible part, and you have exact microscopic expressions for this one and for this one. And if you just sort of arbitrarily decide to set this to 0, then you still have an exact microscopic expression for this term here. And it's perfectly possible to look also at this term.
Yeah, okay, I understand. But I mean, so basically you're arbitrarily deciding to set the dissipation to 0 because this dissipation exists on the same time scale as the reversible part. I mean, that's the whole point.
Yes, so in the paper, we're not setting this to 0. I just wanted to keep the equations short for this presentation here. But I would say this is at least a limiting case you can consider to get some physical ideas.
Well, it's basically the Euler equations in that.
Yes, exactly.
Yes.
I think I've said that as well here.
Mm-hmm. Yeah. Okay.
Yeah, it's the limit where you get the Euler equation. But the Euler equation is a perfectly reasonable model from physics.
Mm-hmm.
So it's an approximation, but there are situations where it's a good approximation. Okay. Then what we require is the entropy functional, or equivalently the dimensionless free energy functional. And another thing that is useful about the Mori-Zwanzig formalism is that it also provides an explicit expression for the entropy functional, or the free energy functional. And in particular, if you consider the case of hard spheres, which was considered by Anero et al., you can derive an exact expression for the entropy functional of non-isothermal hard spheres, expressed in terms of the free energy functional of isothermal hard sphere systems. And that means if you know the free energy functional of hard spheres in equilibrium, and we know this quite well from fundamental measure theory, then by theorems of this form, we can infer what is the entropy functional of non-isothermal, non-equilibrium systems. So this, of course, is a very fascinating result, I think, because it really extends the range of applicability of fundamental measure theory to the non-equilibrium case. And we then further can generalize this result to underdamped mixtures. This will also be shown in our forthcoming article. And so to summarize this part from using the Mori-Zwanzig formalism from the microscopic Hamiltonian dynamics, you can derive DDFT in both of its forms, depending on which variant you use. And you can also derive extensions of DDFT by incorporating more relevant variables. Okay, and then the final thing I'd like to talk about here is the relation to philosophy. The first thing to notice is that if you look at this general transport equation from the Mori-Zwanzig formalism, you can see that by making this assumption about the initial conditions and the Markov approximation, you are breaking on the macroscopic level the time reversal symmetry that the model has on the microscopic level. And thereby, you very naturally get an H theorem for the relevant variables, or for the entropy functional, that you have an expression for it. So you can prove that this reversible term does not make any contribution to the change of the entropy functional, and that the dissipative term ensure that it increases monotonously. And of course, there is a well-known H theorem from DDFT where you can show that the free energy decreases monotonously. And this is contained as a special case in this general H theorem of the Mori-Zwanzig formalism. So in philosophy of physics, there is a great discussion about where does thermodynamic irreversibility come from, because of course the microscopic laws of physics are invariant in the time reversal, so there is no preferred direction of time. So it's an interesting problem to consider, where does irreversibility come from on the macroscopic level. And the Mori-Zwanzig formalism, I would argue, then links DDFT to this general discussions. And I'm going to explain the link between DDFT and philosophy of physics in more detail by using a few examples. Now, first of all, there is in philosophy about a great debate about whether statistical mechanics should be based on ensembles. This is a so-called Gibson approach to statistical mechanics, or whether we should describe individual systems, since this is what in experiments we actually observe, which would be the so-called Boltzmann approach. And if you read review articles about philosophy of statistical mechanics, you sometimes find a long chapter on the Boltzmann school and a long chapter on the Gibbs school, and there are then lengthy discussions about how they are related and which is the correct one. And in DDFT, as pointed out in this article here, there are two different schools, which I've mentioned before, the deterministic and the stochastic one. In some sense, the deterministic DDFT describes the ensemble average of the one-body density. This is why it doesn't have fluctuations. And stochastic DDFT describes the density of a single system. And so these two schools here just correspond to two different variants of DDFT. And therefore, of course, since this relation is well studied in DDFT, it can also give you insight on this more general debate of the Gibson versus the Boltzmannian school. So the second one is a bit more related to coarse graining, namely the problem of irreversibility. Again, there are a variety of schools on that in philosophy of physics. First of all, there are people who say irreversibility comes from coarse graining. So you start from this exact reversible dynamics, you ignore some microscopic details, and you arrive at irreversible macrodynamics. And there are some people who say, okay, this is actually wrong, because thereby you're introducing the irreversibility by hand. And what we really should be thinking about is irreversibility as arising from external perturbations that a system is subject to. That is known as interventionism. So I'm not going to take a position on that here, but again, you can link these both two schools, if you can call it that way, and probably you can call it even more that way here, two different variables about variance of DDFT. So if you apply DDFT to atomic fluids, you're starting from Newton's equations or Hamilton's equations, which are invariant on time reversal. And in this case, to get an irreversible dynamics, as it would be given by DDFT with momentum density, or Navier-Stokes equation with dissipative terms included, then you need to apply coarse graining. Whereas if you apply DDFT to colloidal fluids, where you consider only the colloids and not explicitly the fluid they're immersed in, then you're starting from the Langevin equations or from the Smoluchowski equation, which is already irreversible. And therefore, at least to a large extent, the fact that the colloidal system obeys irreversible dynamics can be attributed to the dissipation that is provided by the solvent. Then there is the case of memory. So a very famous important argument from interventionism is that the typical approximations of statistical mechanics are not justified because they ignore memory effects, and memory effects can, in certain contexts, in spin experiments in particular, lead to motion reversal. And there are then lengthy discussions about motion reversible in spin systems. And motion reversal of not exactly of this type, but also motion reversal has also been described in colloidal systems, namely using power functional theory, which is an extension of DDFT that includes, among other things, also memory effects. And therefore, I would argue again, this could be interesting thing to look at and then to like or to dislike for interventionists. And finally, there's the problem of indistinguishability. So there is a long debate that has started not just with statistical mechanics, but this is going on since medieval philosophy, essentially, whether it is possible that two qualitatively indistinguishable situations are different in some sense. For example, can there be a possible world in which differs from only in that, from ours only in that Julius Caesar becomes president of the USA and Barack Obama conquers Gaul, for example. And in the context of statistical mechanics, we can translate it as, can there be two different situations that only differ in the exchange of two qualitatively indistinguishable classical particles? Quantum case, I'm not going to consider here just the classical one. And there is a recent theory by Wittmann and Alex established in this paper here, which is known as order-preserving dynamics, and which extends DDFT to the case of the single file diffusion. There you have a statistical average in which you can have two configurations that are qualitatively indistinguishable, and that have to be assigned different probabilities. And that, I would say, gives also a hint for this general philosophical debate. And sort of doing this more philosophical or metaphysical problems, of course, I encountered also a physical question that I found very interesting, which is why I want to discuss it a bit further. So the setup we're considering is let's say two distinguishable hard rods in one dimension, which cannot pass through each other. And if you describe that using DDFT, you get an equilibrium state in which the single particle profiles of these two particles are equal, which of course is unphysical because they cannot pass through each other. So DDFT isn't really described caging appropriately. And to resolve that issue, they introduced an asymmetric interaction potential, which then ensures that the equilibrium state of this theory is really given by ordered density profiles. And this is why it's called order-preserving dynamics. And so thing I've asked myself is if we start just from symmetric interaction potentials, so standard DDFT, is it possible to describe the system correctly using power functional theory, so super adiabatic theory, provided that we have the exact power function, of course. So on the one hand, you can say, of course, PFT has to give the correct description because it's an exact theory. On the other hand, you could say, of course, the problem was that DDFT without this asymmetric interaction potential has the incorrect equilibrium limit. And in the equilibrium limit, there is no difference between PCD and DDFT. So how can PFT solve this issue? And the solution that I find most appealing here is that presumably PFT could predict the correct stationary distribution of these indistinguishable particles in one channel, but it would interpret this distribution not as the equilibrium state, but there would in the stationary state be a permanent balance between the adiabatic forces driving the system to equilibrium and super adiabatic forces that keep the system in an ordered state. So that would be, of course, a non-equilibrium steady state driven by superadiabatic forces, whereas for order-preserving dynamics, this would just be the equilibrium case. So the idea of what is equilibrium and is a certain force superadiabatic or not can depend very strongly on the equilibrium framework we employ. So to summarize, I've shown that the Mori Zwanzig formalism provides a very useful route to deriving and understanding DDFT, and also to understand its properties using EDD or in the framework of DDFT that is extended to include additional variables, in particular the momentum density, and also DDFT provides an interesting starting point for problems in philosophy of physics. And I'll then finish with the advertising slide. So of course, the first part is discussed in our review article and this introductory article here. This is about DDFT, this is about Mori-Zwanzig formalism. Then there is this recent paper about the Mori-Zwanzig formalism and general relativity. This not so recent paper about time-dependent Hamiltonians. There is this paper about EDDFT with momentum density, and this paper about indistinguishable particles, which are both forthcoming. And while you're waiting for them, you can also have a look at this paper finally about active matter with inertia. And this paper where I've started to develop a philosophy of DDFT. And with that, I'll thank you for your attention, and I'm looking forward to the discussion.
Thank you very much, Michael.